My great pleasure to welcome Professor Ivelina Georgieva from the Bulgarian Academy of Science and also the Institute of General and Inorganic Chemistry in Bulgaria, in Sofia. So she is a leader in the field of chemistry of materials and thin films, which is obviously a great interest of the London Centre for Nanotechnology as well. And she's part of a collaboration that we've got at with Imperial College London here, the team, and that is led by Peter Petrov here. So thank you very much for hosting this. And that project is a twin team, and it's to look at collaborations between Imperial and the Bulgarian Academy of Science. So I think the presentation today would be about discussing the capabilities available in Bulgaria and some of the science that you do. So it's going to be a great opportunity for the LCN to know a little bit more about what you do. And we look forward to your presentation. And this will be recorded. And so, yeah, available for future reference as well. So thank you very much, and we look forward to your talk.
Okay. Thank you very much for presentation. So kind. I'm Ivelina Georgieva from Laboratory Theoretical and Computational Chemistry of Institute of General and Inorganic Chemistry. This is the leading institute in the area of materials with environmental purpose, general, mainly inorganic materials. And so this is one of the Institute of Bulgarian Academy of Sciences, Chemical, and I'm from Sofia, a capital of Bulgaria, in which the city is ancient, you can see, very ancient, in which it's area of human habitation, at least since 7000 BC. And Bulgaria is a country in the Southeast Europe, located in Balkan Peninsula. I would like shortly present our institute, believing that we can find partners for multilateral and bilateral project and cooperation. So our institute is organized in two departments. One is surface chemistry, including 3 laboratory: reactivity of solid surfaces, electron spectroscopy of solid surfaces, and colleagues from this laboratory, 3 colleagues are here. It's a part of the visiting group, and materials and processes for environmental protection. The second department is chemistry of materials, that includes 4 laboratory: intermetallics, intercalation materials. Sonia Harizanova is a scientist from this laboratory. Crystal chemistry of composite materials, high temperature oxide materials, salt system, and natural resources. And 2 of laboratories, theoretical and computational chemistry and atomic spectrometry methodology laboratory, cover the topics of the 2 departments. So, main research topics in IGIC are systemized in 4 thematic areas: synthesis, structure, and design of materials for clean energy storage, optical and biomedical technology. All these topics are in line with contemporary challenges. And the second one, materials and process for environmental protection and climate changes, including catalytic reaction for purification of emission from F gases. And you can see a lot of topics in this research and utilization of natural resources and environmental monitoring, including assessment of the ecological conditions of polluted nature areas, waters and soils, and so other ones, and new approaches for instrumental and theoretical analysis of materials. The scientific approach is based on correlation, structure, analysis, and properties, which can be useful for prediction of advanced materials. Okay, and due to the successful project in the institute has acquired many equipments and apparatus for synthesis, analysis, and property testing. You can see on this slide main of these equipments. The research activities are reflected on publication of manuscript in indexed journals, about 100 papers per year, and we offer education and training of PhD students on 5 accredited doctoral programs: inorganic chemistry, solid state chemistry, kinetics and catalysis, analytical chemistry and theoretical chemistry. And applied and innovative activities include development of production and technology based on the chemical resources of Black Sea, and organization of the production of the natural medical cosmetics product, which are available in the country and abroad. You can see about the series of the product, and we perform ecological monitoring of Bulgarian soils and waters and services for the company. Currently in progress in the Institute are 37 projects. Substantial projects are National Center of Mechatronic and Clean Technology, and European Twinning and Materials Chemistry Enabling Clean Technologies Twin Team, which are under operative program. And our group, maybe it's better now? Okay, this is ready. Thank you. Thank you. Okay. So our group visit Imperial College London in the frame of the mutual project, European Research Network project, and we are happy that one of the third partners in the frame of this project is Imperial College Department of Materials, and hope this collaboration and cooperation to develop and take to a next level IGIC research capacity. The projects comprises 3 research teams. First one, materials and thin films for environmental protection, from probe molecules to catalytic converters, and the subtopics are heterogeneous catalysis for environmental protection, materials for carbon dioxide capture and gas fuels purification, oxide thin films, and nanostructure for photocatalysis and gas sensor. And our partners are Professor Mary Ryan and Dr. Peter Petrov. The next theme is materials from clean energy storage, including hybrid lithium sodium ion battery, and our partner from Imperial College, Professor Stephen Skinner and Ainara Agordero. And the third topic, the project is ceramics, bioceramics and glasses for better life, which consider tungstate-based optical system and phosphate-based bioceramic. The partners in this topic are Professor Julian Jones and Professor Mary Ryan. And I would like to present our laboratory in more detail, but generally shortly. A laboratory of theoretical and computational chemistry, which consists of five this is the part, the members is eight members, and in the picture, on the picture are a part of the group. The main focus of the laboratory is to develop the theoretical approach for modeling and analysis of materials and processes. And special research topics are design of new optical materials and functionality optimization by molecular modeling of luminescent lanthanide systems and transition metal complexes with optical application. Other special topic are investigation of proton transfer processes, mechanism in ground and excited state, a role of solvent as medium and catalyst, isotope effect, fluorescent markers. These topics match to the approach in the frame of the twin team project. So the metal compounds optical systems are a part of system in which special excited state processes occur as energy transfer, electron transfer, proton transfer upon irradiation in the ultraviolet and or visible region. As a result, the emission properties, finally, the observed emission properties find intriguing application in the area of high technology optics. So, for a progress and develop new efficient optical systems, we need to recognize in depth the processes and mechanism and the relationship between the structure, mechanism, and the observed, finally applicable properties. For that purpose, we need to apply theoretical analysis and quantum chemical calculation. For example, in the lanthanide complexes, we know that to increase the excitation of the lanthanide ions and to increase the luminescent quantum yield, the lanthanide ion have to be attached to the ligand chromophore, which absorb ultraviolet energy and transfer in excited state this energy to the lanthanide ion. This mechanism is known as energy antenna effect mechanism. And this is the scheme of this process. And what we'd like to help to the development of these materials, we would like to apply theoretical approach which can derive this relationship between molecular, electronic structure, physical, chemical, and photophysical properties in order to predict the new chromophore, which have high molar absorbability and form stable and highly luminescent complexes. So generally, the idea to develop this theoretical methodology is based to the applying of advanced computational method and approaches in close relation to the experimental data, spectroscopic data, as diffuse reflection, absorption spectra, excitation, luminescence. So the theoretical analysis and calculation could give us very important information. Some of this information even is inaccessible to the experimentalist. For example, geometry in crowd and excited state, distances between ligand chromophore and lanthanide, bonding strength, character. Also to predict, we can predict mechanism of excited state energy transfer based on the calculated Jablonski energy diagram. Very important to predict the energy of the excited state, character of singlet and triplet state, energy difference for intersystem, which is important for between singlet and triplet for intersystem crossing, also the energy difference between donor ligand and acceptor energy of the lanthanide ion. So, first step of our theoretical approach to choose and validate the theoretical method first in relation to the geometry. We use DFT, ab initio, multi-referent, post-ab initio, semi-empirical methods. And model, also we perform different models approaching experiment, going to different medium, vacuum, solution, solid state, or modeling the molecular, is it is the active material, or when model the absorption of this photoactive unit to the silicate matrix. In this case, we use cluster approach. So our aim is to approach the experiment. And we test and validate our methods, refer to the experimental X-ray structure. This is why it's very important to know to have this information from experimentalists. Also, we calculate vertical excitation energy and all calculated photophysical data also are referred to the experimental data as absorption, fluorescence, phosphorescence spectrum, emission lifetimes. We'd like to be sure that our results is reliable to explain what happened, the mechanism, and to predict the relationship between all this data. So really we in our three recently we have published three papers about this, where describe this process, and our object was lanthanide complexes with phenanthroline, coumarins, and pyridylene dithiocarpamate. So in this approach, we combine quantum chemical calculation for description of geometrical and electronic structure, vertical excitation energy, energies, lifetime of emission, using the Gaussian, Orca, Turbo-Mole, also for periodic system I will consider, we use BAS program. And when we need to predict the luminescent properties and parameter as ligand to metal, energy transfer, back transfer rates, we use semi-empirical calculation based on jet-offer theory of the FF transitions and multi-theories energy transfer. The program which we use is Lumpak. So this is one example of one Jablonski diagram, the terbium phenanthrolene nitrate complex, where from we derive all information of the full, presenting full photo-excited processes from absorption for energy relaxation to the first excited state geometry minimum of the first excited state, intersystem crossing. It's very useful that we can compare the rival photophysical processes of fluorescence and intersystem crossing rates to predict which is more probable to occur in excited state. Also, we can estimate the triplet energy of the triplet state, relaxation to the triplet state, and to estimate the resonance energy between the donor triplet state and acceptor lanthanide level. So this is one example. Calculation. This is other one for European complexes, where also the transfer of energy transfer, the rate of energy transfer and back energy transfer could be also estimated. So these results are described in these three papers. Shortly, I would like to present another approach where the crystal structure are modeled and their optical properties were calculated using periodic approach by means Vienna ab initio simulation package and plane wave set projector augment wave method on the basis of density function perturbative theory and frequency dependent complex dielectric function tensor calculation. We can derive the linear optical spectra for electric field polarization vectors. So this is very good. Our calculated absorption spectrum, very good, agree with the experiment. And when we calculate and also did the band cap in good relation to the long wavelength absorption. When we calculate the total and partial density of state, we can estimate the character of electron transition, which finally is responsible for fluorescence of this pentaethylene diammonium, heptaethylene diammonium, pentadifluorobisulfate, and another approach, the same approach to another object. This is when we consider the effect of urea on arrangement of novel magnesium perinate crystal structure and then optical properties. We also simulate, model the crystal structure of three complexes where the number of urea increased, and find that this increase of urea reflect to the optical properties, the absorption region extent, and we explain that this effect is due to the energy band gap decrease when the urea is 4 in the complex, and it decrease when the number of urea ligands increase to 6 in the complex. So another result is that the conduction band consists of urea, oxygen, and nitrogen states, and this energy of the conduction band, the energy of conductance band increase. So this led to this difference of the band gap, which reflect to the optical. So this is my shortly presentation of the topics of institute, of the scientific thematics of the project twin team, our theoretical topics which are related to the twin team project. And this is my aim, and purpose of my presentation is really to present our researchers, and it is possible to find partner for cooperation and further projects, so we can extend our theoretical study, and in our joint conversation days ago, we found that ONITEP program, which is developed from Professor Hayes, it will be useful for us to know and to use, because will help us to develop the our theoretical methodology concerned to the optical properties. So IGIC is open, our institute is open for cooperation, expresses interest for cooperation in research, and all partners are welcome. So this is a picture from Bulgaria, and I can show this is me in this is a folklore costume in one folk festival. So it's beautiful.
Amazing. Thank you.
Thank you.
Thank you.
Thank you.
Okay, great. I'm keeping an eye also on the chat. Thank you very much for this really interesting presentation, the broad overview, and the more detailed science. So that's been very interesting. Are there any questions on the chat? Huh? Yeah, I'm having a look on the chat. Please feel free to raise your hands or type in. At the moment, I'm not seeing anything, but we can, I'm going to kick off then. In your theoretical description, I think on the europium phenanthroline, you said that you're looking at interaction with the silicate. Is this a surface that, or are you looking at really atomic?
We simulate. Just because the experimental work suggests that they incorporate the European phenanthroline is incorporated in silicate, just to be useful materials for application, and this is why we simulate the adsorption. But we need a cluster which is simulate the surface hydrophilic and hydrophobic surface of the silicate matrix, and hope that the description will be efficient to see what happens if there's some difference, because firstly we after theoretical observation on the complex with the isolated, and after that we'd like to see what happens if there's some difference when this complex is adsorbed on the silicate, and estimate photophysical properties, and my colleague Svetan simulate this adsorption. The real case will be if you take the periodic system of the silicate, but then we have to continue. We can simulate this, but after that we need to treat the photophysical properties, and this large system is difficult to treat for the photophysical calculus. And this is why we use this cluster, okay. And
so it's a finite size. Finite size cluster rather than infinite surface. Okay, but still, do you think that it gives a good representation? Or how does it match with the experiments?
With the experiment, okay. We firstly we refer to the X-ray structure. We compare our model geometric parameters, calculated geometric parameter with the crystal structure to be sure that everything is described very reliable. After that, we have the absorption spectra. We simulate the vertical excitation energy to singlet state and compare to the absorption spectra. In our calculation, we take into account the vibroelectronic also correlation, and simulate our calculations in very good agreement. This is for us very indicative that the method is wise, and we have the fluorescence is very experimental. The fluorescence, we can compare the energy of the singlet state. Phosphorescence, because of the experimental techniques, it's possible to, and depends of the system, if they have fluorescent or phosphorescence, we can compare, simulate this energy diagram, and in which step we compare to the available experiment. And finally, but sometimes there is no experiment, and we explain. The first is to compare and to see that everything's in good relation, but what is the available for the theorist, that we can explain why there is no fluorescence, but there is, for example, luminescence, or what is important, which factors are responsible for this.
And on the surface, what do you see the effect of the surface is on your properties?
Could you explain more? What is the effect?
Well, the major effect of the surface is to kind of, or the absorption on the silicon matrix is to actually restrain part of the degrees of freedom of the luminescent complex, which is supposed to affect the overall relaxation time, and therefore it changes the efficiency as an emitter of the ball.
Does it quench some of the luminescence as well? Or?
Well, in some cases, depending on the type of the substrate, the type of the complex, it leads to quenching, and in other cases, it enhances the rate of radiating relaxation.
Okay.
And we studied a couple of these systems, even though there is a lot of work to do in this field. And there was a serious discussion on what exactly caused this quenching and how exactly the substrate influences the phosphor. But in the end, we saw that it's, in the case of the European complexes which were studied, a case of steric effects, mainly. Of course, we'll need to refine and its explanation in the future.
Yeah, because I'm also aware of plasmon interactions with those molecules, and that's, I think, a topic that we're interested in. Okay, yeah, because I think, Fang and so on are looking at that.
Finally, we can compare the quantum yield in the when the European phenanthrobine complex and is stopped in hydrophilic and hydrophobic. The first suggestion is that when stopped in hydrophilic matrix, the quantum yield should be decreased, but we find that the other factors increase this quantum yield.
Okay, we have a, thank you very much. We have a question from the chat from Anvesh, and he's asking to explain more from the second last slide in the conduction band. So if you,
So maybe the first one example.
Is it the second? Yeah, I think the next one.
Okay. Yeah, the periodic and I don't know what.
I don't know the changes in the conduction band that you were seeing. I guess it was
the change.
Quite,
the change we found that the conduction band consists of oxygen and nitrogen states of urea, and when the number of the urea ligand increase, going from urea 4 and urea 6, the energy of conduction band increase. This is why the band gap decrease. The valence band consists of perennate states, and they are constant. There are no changes in it. This is interesting.
Okay.
This is the effect which lead to the difference conduction.
Okay.
Difference band gap due to the conduction band energy change.
In the energy increase.
Yeah. Energy increase, less negative.
Less negative.
Less negative.
Okay, less stable.
Less
so
negative.
You're destabilizing.
Yes. This why because this the negative and increase gets less negative.
Okay. And the consequences for, hopefully this answers the question. And you're interested in this because these are fairly large band gaps. So I was wondering what the application of those materials was that you had in mind.
Yeah, maybe at the moment I don't know what exactly, but I think that this. For application, maybe this is the new complexes, and in future maybe we develop some applicable to develop this trend applicability.
That was the idea that these complexes, taking into account the width of the band gap, could be used as UV screens, incorporated into UV screen materials.
Okay.
There is still a lot of work to be done here in relation to the question whether they're really suitable for that. But there is some kind of promise that they could be easy to prepare on the one hand, and on the other.
Yeah. So what's the, because you mentioned thin films. So are you thinking about making those as thin films as well as a UV screen?
I suppose that our colleagues that do the experiment would try to deposit them as thin films. We're still discussing this option with them. And also they might be, I'm not quite certain how it is related to biocompatibility, but probably they could be included into some kind of, I don't know, lotions or whatever, which is kind of not quite certain because of the Arabic and so on. But
Yeah, because titanium,
probably,
the titanium oxides are
yeah.
popular, right? Yeah.
So probably a thin film deposition would be the best option for that.
Okay, great, thank you. I'm having another look at the chat, but I think I'm not seeing anything anymore. So no, I don't see any raised hands. Okay, if there are no more questions, no, Peter, no? We can carry on speaking anyway. I look forward to further discussions and also some of discussions about exploiting the minerals and so on. Is really interesting. Last question. I was wondering. So you talked about the theory, which is very interesting and actually relates to a lot of materials that we're interested in here as well. But do you have in your institute also then the synthesis efforts and all of the spectroscopy and so on is happening in Bulgaria? Okay.
But if in our institute, in other institute, in cooperation in different groups.
And you mentioned EPR spectroscopy. Do you also have optical excitation to look at these photophysics and then basically to photo excite and looking at EPR signatures, or is it a...
Yes, we use a lot of just different spectroscopic technique from experimentalists, so from absorption.
I think it's about the EPR spectroscopy. Did I hear right?
Yeah, the electron. Yeah.
EPR.
Yeah.
Okay.
It's not about.
Okay, we have we have a laboratory of EPR, but just maybe this for the special systems.
Okay.
No closer.
Yeah, because it's a good way to.
But they are not in relation to the photophysical properties from laboratory, but not exactly. It is more for the copper. Maybe one there is.
Because we've been using EPR spectroscopy to look at triplet formation as well, and you only see the triplets, you don't see the singlets, so it's quite a good way to look at those Jablonski diagrams that you mentioned.
I think just to estimate if the ion is doublet and unpaired systems, and in the EPR method is appropriate to estimate the environment and how they this is the, I think magnetic, this is EPR, not nuclear, not
it's electron.
Nuclear split,
but
you should certainly look at that.
Yeah.
But most of these complexes in world state, they should have it depends on the type of the lanthanide, whether it's europium or terbium. The general convention is that you take, particularly when you do the modeling, is that you take, you consider that the multiplicity is, I think, 1. And so it's a singlet multiplicity in ground state. But then when it is in excited state, we could probably try that. But we'll have to look at it.
General quantum chemical calculation could be performed from this spectroscopy. If the system is suitable and show this signal for EPS investigation.
Okay.
On Friday we had this talk in White City which was more experimentalist guided and focused. So this is where we discussed more this experimental part or experimental capabilities in Sofia. Today I think the talk was mainly twisted other way around. With mainly focused on the theoretical.
Sounds great.
We prefer to work with the experimentalists, to support the experimental work, to explain properties obtained, and
that sounds good because yeah, excited state calculations are very interesting to us as well. And,
the processes.
And also going from molecules to aggregates. So if you're putting two of those together, their interactions, is this something that you can look into as well, looking at going from the monomer to the dimer, etc.?
This is why we firstly we need information from the experimenters to model how is the isolated or in solution and environment to simulate the environment. If dimers, we can prepare this because there are different effects. First our task is really to know the model to how, and the experimenter can suggest this information. But if not, we can predict if there is no. If we perform some model and there are difference with the experimental and theoretical calculation, we first. Our question is the model is correct? Maybe it's not what we model. We have to prepare environment, something. They are very, but this is very. What is interesting in for the theoretical work that we simulate the isolate to see what is the physical, just the physical property, and then to estimate environment effect, absorption effect, how they perturb the properties which are interesting to be investigated. So and.
Okay, great. No, perfect. Yeah, these molecules on building up from the molecule is definitely also something that we're very interested in. So great. Okay, I final look on the chat. But thank you very much also to the participants online. And especially thank you for a wonderful presentation, very thought-provoking, and I look forward to many collaborations in the future. Thank you so much.
Thank you.
Great.